Welcome to lecture 9 of this course, Advanced Optimization and Game Theory for Energy Systems. Today, we are going to talk about fundamentals of Bender's decomposition. In the previous lecture, we learned how to identify if our problem is decomposable or not. It's either, if it's decomposable, then we can either detect complicating or coupling or linking variable or complicating constraint. So in case we have complicating variable, then we can use Bender's decomposition. Okay, so today we will talk about a bit about fundamentals of Bender's decomposition, and tomorrow we will talk about the potential applications of Bender's in energy systems. And also we will talk about a bit more advanced variant of Bender's decomposition called nested Bender's, which is applicable to multi-stage stochastic programs. But before starting the lecture, maybe in the chat box, you can give me some hint. How are you familiar with Bender's? Have you used this decomposition techniques before or not? Based on or yes and no, I can get a hint. Okay, most of them, most of the answers is no, though there are a few yes. Very good. I got the hint. Thank you. Good. So the learning objectives of this specific lecture is that after this lecture, hopefully you will be able to explain the functioning of Bender's decomposition, the fundamentals of Bender's decomposition, how does it work, and hopefully after that you will be able to implement Bender's to a very simple illustrative problem. Good, but today we are not going to talk specifically about its applications to energy systems. It will be given tomorrow. Good. So this is an example from last lecture, which is about a very simple problem. It's a generation expansion planning problem with two existing generators, 1 and 2, and one candidate generator, unit 3. It means that, well, this is the, I think it's next. Yep. Yes. Our objective function is the summation of expansion cost. So X3 is the capacity of new generator, generator 3, and the operational cost of 3 generators. So 2 generators, they are already existing. Their operational cost is 10 and 25 respectively, while the last generator, which is a candidate generator, if we invest in that technology, its operational cost will be 30. We have the generation limits for existing generators. The installed capacity is 100 and 150 respectively, while for the last generator, it's a variable. If X3 is equal to 0, it means that we are not going to invest in that generator, so its production will be equal to 0. But if we invest in that generator, for example, X3 is equal to 100, then we can produce, but we will have expansion cost. And then we have power balance equality 1 per hour. And of course, our generation expansion decision could not be negative. It's non-negative. Well, so we talked about this example last time, and we realized that there is one complicating variable here. Do you remember what it is? Which variable? X3, exactly. X3 is our complicating variable because if we fix X3, so if we treat X3 as a parameter, not variable, then this term will be eliminated from objective function because it's a constant. And here X3 will be fixed. Then we can decompose the problem 1 per hour, right? So there's no variable linking hours anymore. Then we can decompose the original problem to several subproblems 1 per hour. So if you remember, we had just one complicating variable, which is X3, or linking variable, if you like to call, and the number of subproblems will be equal to the number of hours. Good. So this is a recap from previous lecture. So we have a complicating variable, and it's a good problem to implement Bender's decomposition. Good. Just before continuing, if we have a problem with complicating constraint, but we insist to implement Bender's, what was the trick? Dual, exactly. We can take the dual of the original problem. So if original problem has linking constraint or complicating constraint, its dual has complicating variable, then we can implement Bender's to the dual problem. Very good. For illustration purpose, let's consider a capacity expansion problem like the one we had, but in general, not necessarily that problem. But let's consider a capacity expansion problem in general. First, before talking about Bender's, let's see if we can illustrate Bender's decomposition function schematically. Here, let's say we have a complicating variable. So we would like to plot the optimal value of the objective function of the original problem with respect to the complicating variable. For example, if we assume that our complicating variable is expansion variable, capacity expansion variable, while our objective function is the total cost, which is the expansion cost, the cost of expanding, for example, in unit X3, plus the operational cost all over the hours, across all hours, for all generators, either existing generators or candidate generators. If I plot this function, the function of, the objective function as a function of complicating variables, do you have any idea how does this plot, this curve will look like? Is it decreasing? Is it increasing? Or is it constant? Is it, I don't know, concave? Is it convex? How should it be? Achilles says it should be something like convex. Something like this, Achilles. Not here because let's start from 0. Should be something like this. Peter says parabola. Brian says convex. Goran says decreasing. So is it something like this? So maybe Achilles, you can explain why you think it should be convex. Farzad says like the first one. So something like this.
Okay, so, well, I'm not sure that it will be a parabola, but since the original problem is convex, I would assume that it will be convex, this graph. It could be
either
also
parabola or not this, but or it might be, let's say, linear, something like this, not necessarily.
It could be linear since it has some constraints, so it might be a straight line, yeah.
Yes. Okay, so why this? Why convex? Why decreasing here? Why increasing here? Achilles?
Just from intuition, because the original problem is convex, and I would assume that there is an optimal.
Okay, let's go with this description. Here, the capacity of new generator is 0. And we are talking, let's say, about supplying demand in 20 years from now. So then we don't have expansion cost. We only have operational cost because our expansion decision is 0. But probably the operational cost is high because we have deficit of generation capacity. We need to have load shedding. We don't have enough capacity to supply demand. Is it clear? Yes, Brian is talking about underinvestment and overinvestment. Exactly. So by starting investing, for example, if we invest 10 megawatt in the new generator, in the new generation asset, of course we have some expansion cost, but also we are covering supplying more demand. So in general, we have benefit. So here it's the part that we have underinvestment until some point. And after some point, by adding more new generation units, we are just incurring more expansion cost while the demand is fully supplied. So there is no sense to add and more install capacity, right? So Sahand said it's a trade-off between operational and investment cost. Tamas said high curtailment cost on the left, high investment cost on the right. All of them, they are 100% correct. So is it clear for everyone that we can assume we have a convex function? It could be quadratic, it could be linear, but what it is, it's convex. Very nice. So let's say that our objective function is quadratic, so we end up in this kind of curve. Good. And we have an upper bound here. It means that we have, let's say, budget constraint. We cannot invest in more than, let's say, 200 megawatt. It's a budget constraint or whatever. Good. So I hope everything's clear so far. So here, as many of you explained here, the expansion cost is low, operational cost is high due to capacity shortage. We have under investment issue, so it's good to, I mean, that's why the total cost is decreasing. While here, expansion cost is high, we don't need to have more install capacity, then it's a overinvestment. So what point does provide a trade-off for us between operational cost and expansion cost? Which point? The minimum, exactly. So here is the best, let's say, for example, the corresponding expansion decision is, I don't know, for example, 70 megawatt. It's optimal to invest in new generation capacity 70 megawatt because its corresponding expansion plus operational cost is the minimum. It's clear, right? Very good. So this point provides us a trade-off between expansion cost and operational cost. But now let's do one thing. It was a very trivial question because we had this curve. We had that curve and we easily identified, this is the optimal point. 70 megawatt is the optimal point. But now let's assume that this curve is not given, though it's dotted. I mean, it's a dotted curve, but assume that you don't see it. We don't have it. So do you have any idea how iteratively we can achieve the optimal solution, which is here, 70 megawatt? So you don't see this curve, but you can do some iterations, some calculations in iterative. Akila says gradient descent. Yeah, I agree. Yeah, I got a lot of answers, gradient descent. And Peter says, if convex, we can use Newton-Raphson. So good. Yes, I agree. Yeah, but what I'm gonna explain is the same thing. What we can do, let's say we are in iteration 1, step 1. Let's choose one arbitrary value for complicating variable. For example, let's say 40 megawatt. It's arbitrarily choose in the first iteration, right? And then we can calculate for 40 megawatt, how much the total cost, the operational plus expansion cost will be. We can do that, right? So we can say that for 40 megawatt, I mean, the cost is this. So we got 1 point over the curve. Good. But can we get any other information out of this? So for 40 megawatt, the total cost is, let's say, $10,000. Can we get any other information out of this point? A slope. Abul Faz says slope. How can we derive a slope? Yeah, the systematic way is, as Goran said, it's just to check dual. But numerically, you can say 40 plus 0.01 and 40 minus 0.01, calculate the right and left hand side sensitivity, and it will give you the left and right hand side sensitivity. If it's convex, hopefully then the two side sensitivities, they are equal. Anyway, you can get slope. Okay. Yeah, Johan also said very nice. If we go for gradient descent, we can also see if the minimum is in the right-hand side or left-hand side. Also, it's a very good answer, Johan. Good, but I think hopefully you are convinced we can also derive slope. If we can derive a slope, what we can do, we have one point, we have the slope, so we can draw a line, this red line. Do you agree? We have one point, we have this slope, we can draw a cut. I mean, later, instead of this line, I will call it cut. So I draw a cut. Do you agree so far? It's possible, right? Good. So now I don't see, remember, I don't see the green line, the green curve, but I see the red line, the red cut. So, and I stop the red cut here because it's the maximum complicating variable that I can take. So it doesn't go to infinity because I have a budget constraint or whatever. So if my total cost is like this, what is the optimal expansion decision? If the red curve represents the total cost function, what is the optimal value for investment? What is the maximum? Exactly. We are minimizing the cost, not maximizing. So here is the optimal, because here our cost is minimal. Very good. So what we can do, so now we are in the iteration 2. So this time we are not taking a guess. We systematically find the optimal investment in the second iteration, which is this point. Again, we repeat what we did in iteration 1. So we calculate the corresponding cost. Also, we calculate the corresponding slope, right? And here we don't have right-hand side slope because, it's outside our feasible space. So what we can do here, we achieve this point, we achieve this slope. So I can draw another cut, right? So if I do, I will achieve this in the iteration 2. So John said if both left and right-hand side results with sensitivity are higher, then the point would be the minimum, Jalal, right? Yeah. In the, yes. Good. Now we are in end of iteration 2. So what is the next one? Now these two lines, these two cuts represents our cost function, right? And remember, we are trying to minimize the cost. Where is the optimal point, optimal complicating variable this time? Yes, interception of the red lines here. So now here is our optimal complicating variable. Let's say, I don't know, it's 45. Again, we repeat what we did. So if we repeat what we did, sorry, we will end up to this curve. So by this iterative process, what we are doing, so Prabhat asked, can you please explain how you took the second cut? Yes, definitely. So we have this cut, right? So from 0 to 100, this is our decreasing cost function. And if we know that our cost function is just this red light, our optimal complicating variable is here because the corresponding cost is the minimum, right? So we pick this point, but we realize that, oh, the corresponding cost is not here because this curve is not correct, is not accurate. The corresponding cost not here, but it's here. So based on this point and its slope, we draw another one. Is it clear, Prabhat? Yes. Okay, let me see the chat box if you have any other question. He said, this reminds me the concept of support hyperplane. Any relation? Well, let's see. Ahmad says, creating the curve. Exactly. So what we are doing by repeating and adding more and more cuts, we are restoring our original green line. So we are trying to construct the real cost function. Exactly. As Barbara said, we are approximating the objective. Very nice. Johan said approximating the curve. Very, very good answer. And we have a lot of also correct answers. Very good. Very good. So as you said, we are constructing or approximating the original cost profile. It means that the dotted line, we are approximating it or constructing it by using cuts. And more iterations means more cuts, means that more accurate cost profile. And this is exactly how Bender's decomposition works. Is it clear? Yep. Is it clear? Yes. Any questions so far? No. What about this? If our original cost function with respect to complicating variable looks like this, does the method I explained work? Peter says no. Goran says no. Sahan says maybe. Many no. Yannick says local optimal. Very good answer. Good. Tomasz says find a local optimum. Exactly. We can start, use the same method, but as you said, we may stuck to this point or this point. If you are minimizing, not here. Instead of here, we may be stuck here. So we may end up to a local solution, as you said. So if the original cost function or the value of objective function as a function of complicating variable is, if it's non-convex, then our iterative cut-based method does not necessarily obtain the global optimal solution. It's clear, right? So this is why it's my last slide, but I can reveal now. Bender's decomposition guarantees convergence to global optimal solution only and only if the original objective function as a function of each complicating variable, if it has convex, convex curve. Ahmed says, so in general, the objective function doesn't have to be convex, but only with respect to complicating variable. Yes, I totally agree. We may have, we may end up in a very, I don't know if it's possible or not, a specific case that the optimization is non-convex, but its value to a complicating variable is convex. I don't know if it may happen or not, but yes. For Bender's, the value of original objective function with respect to complicating variable should be convex. Sansei does not guarantee finding the global optimal for MILP. No, there is no guarantee. Brian says, how will this curve look if we have more complicating variables? The same, just you are adding the third dimension. If you go for a complicating variable, then instead of a curve, you go for a plane, but the same story. The same story. So your objective function with respect to each complicating variable should be convex. Should have convex envelope. Did I answer, Brian, to your question? So if you have two complicating variables, this profile, you can go for a plane. It's a three-dimensional, let's say, figure. Still, it should be convex.
So then you said for each complicating variable, then you don't need to plug 3D. You just need to plug 2D always. I'm confused.
No, by each complicating variable, I was talking about, you are not fixing the other one. So if there is two complicating variables, you plot a 3D. So let me correct it.
Okay. Okay, thank you.
Good. Good. So the answer is no. And references. Again, you can use this very nice book. One of the chapters is about vendors decomposition. So also my example in the remaining slides, it comes from this book. First, I will explain you how vendors works, and I will use an example, a numerical example, a simple example from this book. But later in the second part of this lecture, I will explain what is the principles of vendors decomposition. And for that, I use this very nice paper. It's a paper published in 1991 from, the first author is Pereira from Brazil. I really like that paper. Good. Any questions so far? No. Good. Let's go for this very simple optimization problem, linear program. I know we don't need to solve it by decomposition. It's simple. We can even solve it by hand. But to understand how vendors works, let's use it as a starting point. I promise you later we will go for much complicated problems that we can solve for vendors. But I think to start, it's a good problem. So let's say we like to solve it by decomposition. Again, as I insisted, you can solve it directly. We implement vendors to this problem just to learn how vendors works. We have only two variables, x and y. We don't have really a complicating variable. I mean, it's a simple problem. But to start, let's assume that x is our complicating variable. Okay, it means that we can fix, we can give a fixed value for x in the first iteration. If we do so, we will end up to something that we call it subproblem. Let me back here. So we fix x to, we replace x with parameter x fixed, so it can be removed from the objective function. So this is why in the subproblem, we have only the other term, minus y. What is superscript I? It's the index for iterations. So it's the variable y in iteration I. So I is our current vendor's iteration. And we will see later that k is also set of our previous iterations. For example, if we are in iteration 4, so I is 4, while k is 1, 2, and 3. Let's get back to here. Here, the first constraint, now x is fixed. So we can move it to the other side. So it will become y is lower than or equal to 5 plus x fixed, right? Like here. So y is lower than or equal to 5 plus x fixed at iteration I. So this is the fixed value of x in iteration I. And y is our variable in iteration y. Good. And pi I is the corresponding dual variable of that constraint in iteration I. Clear? We do the same for other 3 constraints. So the corresponding term for x moves to the right-hand side. And we have those in the subproblem. This constraint can be removed, right? And remember, we have to fix x in a point which is feasible. So x should be fixed in the first iteration in a value which is a feasible. For example, we can fix x to be 12, but not 17. And this constraint can be removed from subproblem because x now is fixed, but we keep this constraint. So is our subproblem clear? If you say clear, I'll continue. Very good. Good. So this is our subproblem, and we have 4 dual variables or sensitivities. Let's see what our master problem will be. Can you guess what the mission, the objective of, not objective, with master problem, what we are trying to do? Any idea? Subproblem determines the optimal value for y for given x. But what does master problem do you think? Any guess? I'm repeating. For given x, subproblem finds y. So what does subproblem should do? Yes, find x, exactly. So the objective or the goal of master problem should provide the updated value of x fixed over iterations. Let's see how does it look like. Before me to explain what master problem is or why do we have this formulation, maybe you can spend 1 minute to try to understand what objective function and different constraints of the master problem are. So I give you a minute to think of. John says, what does alpha represent, Jalal? Actually, it's my question to you, John. What is alpha? Ahmad says, are those the cuts? That's my question to you. Kelly says, a part of the Lagrangian. Brian says, approximates the value of the subproblem. Abulfai says, auxiliary variable. Sebastian says, I think Kelly might be right. Nuran says, lower bound. Okay, I think you thought enough. Let me continue. Let me start with objective function of the master problem. So yes, we have a new variable, which is auxiliary alpha, but again in iteration I. Let me get back to the original problem. In the original problem, the objective function is minus y minus x over 4. Remember that? And here it's minus x over 4 plus alpha. What alpha does represent? It represents minus y in the original problem, which is also appeared in the subproblem. Right? So alpha represents the objective function of the subproblem in this case. If we have 2 subproblems, it represents the total objective function of the 2 subproblems. We will see that, but okay, it's a complicated one. Let's focus on this one. So yeah, Farzad, we will talk about these signals or whatever. Let's just try to discover what this master problem is. So we understand what alpha represents, right? It represents the value of subproblem or the value of a part of the objective function, original objective function, which appeared in the subproblem. Good. What about this constraint? What is that? Original constraint, exactly. Oops, sorry. Yes, remember in the original problem, we had this constraint that we removed when we fixed x. So now we need to restore it in the master problem. Exactly. So this is our original constraint. Very nice. What about this constraint? Why do we need it? Let's say alpha down is minus 10 to the power of 6. Farzad says, because we minimize, it's going to be unbounded without it. Is it unbounded? We have the last constraint. Good. Farzad, yes, also Nuran answered correctly. I'll talk about the last constraint later, but the last constraint is until the last iteration. So if we are in iteration 1, I minus 1 is equal to 0, it means that in iteration 1, we don't have the last constraint. So in iteration 1, we are minimizing alpha, and alpha has no lower bound. So we need a constraint to provide a lower bound for alpha just in the first iteration. And to not affect the optimality of alpha, so the lower bound should be a very big negative value. For example, minus 10 to the power of 6 or whatever. So it's just to avoid unboundedness in the first iteration. Good. But most importantly, I don't expect you to exactly say why does it look like this constraint, but well, we know what alpha is. What about the right-hand side term? Is it something which is familiar? Nuran says Lagrangian function. Is it Lagrangian function, Nuran? Dual objective function. Very good, Amos. It's dual objective function. Exactly. The dual objective function of what? Which problem, Amos?
Give me a second, of the sub-problem.
Yes.
Because we want to find a bound for the sub-problem that we put into the
exactly. If you derive the dual objective function of the sub-problem, you will have exactly this term. Okay, forget about k and I as iterations, but this is exactly the dual objective function of our subproblem. So if you remember, our objective function of dual will be pi times this term with a sign minus, with a minus sign. Do I need to derive dual function, or you think it's easy, it's understandable? Minus mu times the constant part of the second constraint and so on. Is it clear? Yes. Very good. So we are here with these constraints. We are just saying alpha in iteration I is greater than or equal to the dual objective function. So the dual objective function in the previous iteration, yeah, I will explain what k and I is, but later. But so far it's enough. I will explain later. But what this says, k is all the previous iterations. So if we are, as I said, in iteration 4, k goes for 1, 2, 3. If we go for iteration 5, k is 1, 2, 3, and 4. So what are we doing? Shall I say that, exactly, can I say that in each iteration, I'm adding one additional cut? Exactly as John said, adding cuts in each iteration. And I will call these constraints Bender's cuts. Bender's cuts. And remember, with these cuts, we are trying to reconstruct the, reconstruct the profile of alpha as a function of x, which is the same as objective function of the subproblem as a function of x. Clear? Is our cut linear or nonlinear? Our cut function, the last constraint. Is it linear or nonlinear? Okay, remember, though this is a dual variable, but it comes from the previous iterations. So it's given, it's parameter. So only variables are those x and alpha in the current iteration I. Whatever we have with k, it's given. It comes from the previous iterations. So it's a parameter, 5 parameter, xi is a variable. So this term is linear, and the same for others. So our cut constraint is linear. But why do we have k here? Why do we have I here? It will come in the second part of the lecture. I will prove it. So what I ask for you is that so far, accept the cut as it is here in the slides. In the second part of the lecture, I will explain you why cut is something like this. Good. Kelly said, are the Bender's cuts defined for all I? But yeah, I mean, I is the iteration number. So k, yes. So if we are in iteration 4, we have 3 cuts. If we are in iteration 5, it means that if we are in iteration 5, we have 4 cuts, right? But if we are in iteration 4, let's say like this. Let me explain better. In iteration 2, we have cut 1. In iteration 3, we still have cut 1. It's unchanged, but now also we have additional cut number 2. If we go to iteration 4, we have the same 2 cut 1 and cut 2. They are unchanged, but now also we have additional cut 3. Is it clear? Yes? Kelly said, can you explain again the necessity of the constraint with alpha down? Definitely. Here is iteration 2. I started with iteration 2. But what about in iteration 1? In iteration 1, how many cuts do we have? 0. We don't have any cut in iteration 1. So in iteration 1, we don't have this constraint. So now we are minimizing alpha. If we don't put lower bound for alpha, alpha's optimal value will be -infinity. So we put alpha down to make the problem not unbounded. Carolina says, if we have multiple subproblems, we'll have multiple alphas. No, we will still have one alpha, but the summation, yes. I'll talk about the multiplicity of if we have more subproblems. Always we have one alpha, but alpha will represent the total objective functions of all subproblems. So always alpha is 1. It means that in every single iteration, we are adding only one alpha, or one cut. Yeah, SNL is talking about multi-cut version. I'll talk about it, not today, tomorrow. Let's talk about conventional benders. Clear? Any questions so far? I hope it's clear. Good. So alpha, as I said, is auxiliary variable, represents the objective function of subproblem. If we have one subproblem or if we have multiple subproblems, it represents all subproblems within the objective function of the original problem. As I said, alpha down is just to avoid unbounded solution in the first iteration. We can go for a large negative value for that, like -10 to the power of 6. If it's large enough. And the last one, we will call it Bender's optimality cut. I'll talk about optimality later, but this is Bender's optimality cut, right? We have one additional cut in each iteration. I can explain here why we are calling it optimality. Because here we assume that for given x in the subproblem is feasible and we could derive dual variables to be up here in the cuts. If our subproblem is infeasible for given x, then we don't have values for dual variables. Then we need to add something called Bender's feasibility cut, not optimality cut. But it's something that to be honest, I don't recommend based on my past experience. I try to implement it. It's not very well functioning in my understanding. So my suggestion is that if for a given x, you saw that your subproblem is infeasible, add slack variables. And I already explained what slack variables are. You can, for example, here add plus alpha, not alpha because we used, so beta plus 10 to the power of 6 beta. So you are penalizing objective function to make sure as much as you can, beta will take value 0. So by that, you can make your problem always feasible. Sebastian said, does degeneracy in the primal problem affect Benders? So for example, price multiplicity, I would say no. I would say no. Good. Hopefully everything is clear. But what the algorithm is, you can imagine, we can start with initialization. We go for a fixed initial guess for complicating variable, while we assume that the lower bound is minus infinity. Then for given x in iteration 1, you see this superscript is iteration 1. For iteration 1, we solve subproblem or a set of subproblems if we have more than one subproblem. And the value of objective function of subproblem, or if we have two subproblems, their summation, the summation of two objective functions we achieve for each subproblem, it provides us upper bound. So lower bound is minus infinity, upper bound is the optimal value of subproblem, the objective function. We check if their difference is lower than or equal to epsilon. Epsilon is I don't know, for example, 10 to the power of minus 3 or whatever. Then we have the optimal solution. So it means that our x fixed is the optimal value for x. But if not, then we go and solve master problem based on the sensitivities we got in the subproblem. We add Bender's cut and we find the updated value for the complicating variable. And also we derive the value for auxiliary variable. The value of alpha gives us the updated lower bound. Now we have updated lower bound, which is not anymore minus infinity. Now with the updated x, we go back to step 1 and we repeat it until lower bound and upper bound, they converge. Is it clear? Barbara said, is the solution different if we choose y to be our complicating variable instead of x? No, no, no. Always, the solution of Bender's is equal to the solution of original problem as long as the original problem is convex with respect to complicating variables. So we are not expecting different solution out of Bender's compared to original solution. Okay, good point, Barbara. I see that the time is over, but I like to finish in 5 minutes. I would like to also present an equivalent compact form of Bender's. It's not different, it's still Bender's, just a bit different formulation. It's equivalent, you will see. Now this is my subproblem. Can you detect any difference with respect to previous subproblem? Brian says X now is also a variable. Nuran says without alpha. Alpha is in master problem. I'm talking about subproblem. In subproblem, we didn't have alpha. Barbara says the last constraint. Very good. Here, instead of saying X is fixed, I fix X as a fixing constraint. It's the same thing. So I treat X as a variable, but it's artificial because I fix the value of X to be fixed to X fixed in a constraint. It's the same thing, right? I'm not doing something differently, right? Do you agree? It's equivalent to the previous subproblem. But the nice thing is here is that now I don't need any more these dual variables. What I need is only single dual variable. So if your X is appeared in 1 million constraints, you need to derive dual variables from 1 million constraints and put it in the Bender's cuts. But this is a trick. Here, I don't need any more these dual variables. What I need to pass it to master problem is just rho. Clear? John says why? Okay, I can explain here. Here we have 4 constraints in which X is appeared. And you need to write all of them in the master cut. If instead of 4 constraints in the subproblem, including X fixed, you have 4 million constraints like that, then your Bender's cut will be so long, right? But here I do a trick. Just what I will need here to pass it to master problem is just rho. And how does the master problem will look like? The objective function, let me change the color. The objective function and the 2 constraints, they are unchanged. Now, again, we have 1 cut per iteration, but it's simplified a lot. It's simplified a lot. Clear? It's the same. Why it's the same? It's my question to you. It's the exercise. But I will call it compact form, if you like. Okay? So this is my question. I gave you 2 forms of Benders. The first form and compact form. It's obvious that subproblems are the same. But why the master problems are equivalent? Why this master problem with this cut is equivalent to master problem with this cut? That's my question to you as exercise number 1. And the guide is how you can check the 2 optimization problems are equivalent. Just check KKTs. Okay, so I like that you think and prove mathematically why those 2 master problems are equivalent. And second, as you can expect, provide a code for the previous problem. It could be in GAMS or Julia or Python or MATLAB or whatever. But tip, always make sure that, because here we need dual variables to get from subproblem and to pass it to master problem. Always please make sure that the sign of your dual variable makes sense. As I said, for example, if for inequality in a standard form of subproblem with minimizing, constraints are in the form of lower than or equal to. If you get negative values for dual variables of inequalities, then your your code reports wrong dual variables with the sign. So please make sure that it's okay. Sand asked, why is the compact form better? Is it more computationally efficient? No, I didn't say that. I explained, because formulation of Bender's cut in the compact form is easier. Instead of writing 1 term related to the constraint appeared in subproblem, you always have way simpler formulation for the master cut. So computationally, they are the same. Just this is easier to formulate. It's equivalent. Okay. So I hope the two exercises are clear. And after a break, I will explain you why we write Bender's cuts in that form. Right? But you already detected that in the original Bender's, the right-hand side of Bender's cut is the dual objective function of the subproblem. You already got it. Later, I will show you why it looks like that, why it should be like that. The time is over, so I skip questions to have 10 minutes break. Then we will start with your questions. Okay. Right now it's 5:12. We can start it at 5, let's say 25. So 30 minutes break. See you in 13 minutes, now 12 minutes. Okay, let's continue. Before continuing the slides, I can take a few questions. I see Brian asked in the chat box, why is the master problem a lower bound and the subproblem an upper bound? Good question. Let's get back to formulation. Yeah, here. So Brian, in the first iteration in a master problem, as I said, the Bender's cut, we don't have a Bender's cut, right? So what is the optimal value of alpha in the first iteration of the master problem, Brian? Maybe you are not.
Alpha down?
Alpha down, yes, alpha down, which is minus 10 to the power of 6, right? Good. So alpha in the first iteration is minus 10 to, sorry, let me write better. Alpha in the first iteration is equal to alpha down, which is a very large negative value. Then in the second iteration, what happens? We are saying alpha in the second iteration is lower than or equal to the right-hand side, which we know that it represents the objective function of the dual problem, sorry, the dual objective function of the subproblem. And if strong duality holds, the objective function, the dual objective function of the subproblem represents the primal objective function, right? So as you see, we are starting from a very lower value, minus 10 to the power of 6. And then we are trying, it's a Wick duality. We are trying to reconstruct the value of the objective function of the subproblem through the dual objective function. And we know that always the dual objective function is lower than primal one. It's a Wick duality theory, except in the optimal point, which are equal. Am I clear?
Yeah, makes sense.
Yes, so this is why always master problem is the lower bound based on the Wick duality theory until the optimal iteration in which the dual objective function of the subproblem is equal to the primal objective function, then alpha represents minus y. So this is why master problem is always lower bound while the subproblem is the upper bound. Is it clear, Brian? And is it clear to everyone? Priyanka said, related to Brian's question, if the subproblem was minimized y, then would it give the linear bound instead of upper bound? Let me understand Priyanka's question again. If the subproblem was minimized y instead of minus y, you mean? Then would it give the LB instead of UB? Yes, yes, definitely, yes. Yes. but we don't need to do that. Why should we do that? Okay. Any question else so far? So kind of I relieved the math behind Bender's decomposition. You can imagine what it is. It's based on duality theory, but yeah, let's talk more about that. So I'm following the paper I introduced in the beginning slides. It's a paper by Pereira et al., published in Mathematical Programming in 1991. I'm using that paper to explain Bender's decomposition. Let's consider a very, sorry, a very simple linear program with two variables, x1 and x2, right? Let me assume that x1, it's a deterministic problem, but let's assume that x1 is the first stage variable, and x2 is the second stage variable, though it's deterministic. So we can say that the first term in the objective function is the first stage cost because it depends on x1, which is the first stage variable, and the second stage cost. Also, you can call it future cost if you like, because it's the cost of future in the first stage. Then the first constraint only includes x1, so we can call it first stage constraint, while the last constraint includes both x1 and x2, and we can call it linking constraint, the constraint that links x1 and x2. It's just terminology. Yes, again, we can solve this problem in one shot without decomposition, but as a practice, let's try to solve the first and second stage problems separately. Okay. Good. If I separate this original problem to first stage and second stage problem, what it happens? So first stage problem is, the cost is C1x1. Let's recall this second stage cost. Let's recall it alpha 1, which is a function of x1. I'll define what it is, subject to only the first stage variable. And then how can we define the optimal value of alpha 1 x1? Alpha 1 of x1 is the second part. We are minimizing only over x2. The second cost, the future cost, the second stage cost, subject to the linking constraint. And why is it a function of x1? Because also x1 appeared in the second problem. So for given values of x1, if you like to say, we can solve the second stage problem. We can find the optimal value of alpha, and then we can put alpha here. Is it clear? Good. Very nice. But as I said, x1 as the first stage variable, it appeared in the second stage problem. So still we cannot solve them separately, because to be able to solve this, yes, the first stage is fine, though we don't know what this function is. And in the second stage, to be able to solve that, we need to know what the optimal value of x1 is. John said, what does E1 stands for? Which E1? Here, E1 is a parameter just. So it's in the original constraint, E1, A2, B2, all of them, they are constraints. Sorry, they are parameters. We only have x1 and x2 as two variables. So A1, B1, E1, A2, B2, C1, and C2, all of them, they are parameters. Good. So still we cannot solve this problem separately, right? Because we need to know what the optimal value of x1 is. And then after that, we can solve the second stage problem. After that, we can solve the first stage problem. So still we cannot solve this problem separately. But do you have any potential approach to solve the first and second stage problems separately? Any idea? Not necessarily in an iterative manner, in one shot. Any even a stupid approach. Nuran says we can assign trial values for x1 and solve the second stage and solve first stage variable. Exactly. So you can assume x1 is a parameter and you can assign it, I don't know, 1 million variables, either 0 or 1 or 2, blah, blah, blah. And for each of them, you can solve this, the second stage problem. Then you can derive a function for alpha. So you can say alpha 1 as a function of x1, as a function of x1, I don't know, has a function, something like this. Then you numerically obtain this function, and then you can plug it here. That's the simplest approach, right? That one can think of. So as Nuran suggested, we can discretize x1 into a set of trial values. Yeah, let's say n number of parameters. So for each given value of x1, we can solve the second stage. We can save the value we achieved for alpha 1 of x1. We can repeat this for all x1s. We can derive a function, and then we can include that function in the first stage problem. So it looks like this. We have the second stage cost, future cost, as a function of x1. It looks like it's not dynamic programming, but it looks like a dynamic programming approach, right? It means that the first stage variable, you try to anticipate the future cost. But what is the main drawback of this technique? I understand that it's very, how to say, not very, any clue? Nuran says, or Drake says, we don't know which x1 to pick. I think you're talking about the generation of initial values for x1, right? How many x1 we should generate? 1 million, 10 million? Nuran says trial values may not be known. Too many trials may be needed. Exactly. Akila says, don't know where to start. Well, it's why we know we can start by generating 10 million values for x1. That's the initial point. Yannick says a lot of model runs. I totally agree. Lisandro says a curse of dimensionality. Very good wording. Yes. Carolina says because we don't use continuous values for x. Yes, we don't know, but we can interpolate and we can generate a cut, right? We can do some mathematical works. So it says that, okay, for different values of x1, I got the values and then I'm connecting the stats. Something like that. And of course, if I have more values for x, more simulations, then I can construct the future cost more accurately. So as you said, it needs to discretize the decision variable x1, which results in computational issues. For example, if we have 10 decision variables, so 10 x1, if you assume x1 is a vector of 10 variables, and if we go for just 4 trial numbers for those 10 variables, it means that we need to solve the second stage problem 4 to the power of 10 times. It's insane. Is it clear? Good. Any alternative solution approach? Something more elegant? Any idea? A bit better job? This is the question Mr. Benders thought of it, I don't know, 70 years ago. How can we solve this problem in a more elegant way? Not numerically, but analytically. Let me continue. What we are gonna use is a technique that we call it dual dynamic programming. If you go, you can call it DDP, dual dynamic programming. So this time, in the previous slides, we tried to approximate the future cost, the cost function alpha 1 of x1 numerically. Let's do a better job and try to approximate it, not numerically, but analytically. Okay? How can we do that? It's easy. Remember, this is our second stage problem, right? And it's a function of x1. And let's say that we have only one constraint here. You may have more than one. It will not change the problem. And let's say pi is the corresponding dual variable. Okay. Without loss of generality, let's assume that both x1 and x2, they are non-negative, but you can relax it. It will not change the problem. Okay. So from your knowledge from the first lecture, maybe you can help me to derive the dual problem of the second stage problem. So remember, we need to first derive the Lagrangian function. So it's a Lagrangian function as a function of x2 and pi, right? Remember, x1 is given, is equal to, let me write below because I need a space later. So our Lagrangian function is c2x2. We need to make it in a standard form, lower than or equal to. So it's b2 minus e1x1 minus a2x2 is lower than or equal to 0. So our Lagrangian function is plus pi p2 b2 minus e1x1 minus a2x2. That's it. It's our Lagrangian function. How can we derive dual problem? Remember, we need to minimize this over primal variable, which is x2, and then maximize over pi. Do you agree? I'm trying to derive the dual function of the second stage problem. And if we derive it, it will be eventually max over pi. By the way, I forgot to say also, we assume that x2 is non-negative. So let's say plus mu times minus x2, right? Because we assume that x2 is non-negative. It's additional constraint. You can also remove it. It will not impact. So it's maximized over p. Our constant functions in the inner problem, for the inner problem, is b2 and this term. This part for the inner problem, they are parameters. So we keep it in the objective function of the dual problem. So it's maximized b2 minus e1 x1. And here times pi, right? And here our constraint, we can take KKT over the inner problem. It's C2 plus pi minus A2 x2 minus mu is equal to 0. Do you agree? Nice. And here again, just to go for an elegant formulation of here, of course, we have pi and mu, but we can eliminate mu because it's non-negativity condition. So we can eliminate mu, we can remove it. It's minus mu, so it means that without mu, it's greater than or equal to 0. Yeah, this is our dual problem. And pi is, of course, positive. Thank you. Thank you, Barbara. Yes. Priyanka says without x2 in the constraint. That's the whole point. Thank you. You're not thinking like vendors, Priyanka. We will see. So as I said, this is the dual problem, right? We derived it together. Sorry. Let me change the color. Any questions so far? Is it clear? Everything clear? Maybe you can write in the chat box, it's clear, then I can continue. Very good. Okay. If the in the optimal solution, if Slate conditions hold, the strong duality theorem says the original objective function, here is alpha 1 of x1, is equal to the dual objective function, which is in the optimal point. So this is why I put a star. And remember here, B2 and E1, X1, they are constraints. So as you see here, A1, alpha 1 as a function of X1 is equal to P star at the optimal point times B2 minus E1, X1. X1, it's not necessarily, it's a given. It's not necessarily optimal point. And as Priyanka said, now the future cost is a function of only X1, not X2. So this constraint says that there is a linear relationship between X1 and the future cost if the optimal value of pi is given. Is it clear? So this is, remember, this is the strong duality, but the weak duality says that alpha 1 of x1 is greater than or equal to pi. Pi doesn't need to be necessarily optimal, b2 minus e1 x1. This is weak duality. While in the optimal solution, we have strong duality. Very good. So this is the constraint, the equality, strong duality I picked. And as I said, in the other points in the feasible area, we have weak duality. Hope everything is clear. But the challenge is that still we don't know what the optimal value of pi is. Good. Again, this is my strong duality, our strong duality equality. Remember last time we discretized x1. But what if we do something similar? This time we discretize the values for pi. We know that it's non-negative. So we can do maybe something similar. We can derive n number of trial values for pi. And what we can do next, we can generate a problem like this. So for n number of pi's, so they are given. And the second part appears or repeats in all constraints. So let me, maybe you can think for a minute what this optimization problem is. Maybe you can answer me. If optimal pi is one of those we discretized, for example, if pi2 is the optimal, does this optimization problem achieves the above equality or not? Please think what this optimization problem does. Nuran says yes. Akles says probably it's a polyhedron with p star being one vertex. A pi star, yes, being one vertex, exactly. Is it the min-max? No, it's not min-max. Hosna says the minimum alpha is. Very good. Let me give you an example. If I say minimize alpha, alpha is a variable, alpha is greater than or equal to 10, alpha is greater than or equal to 20, and alpha is greater than or equal to 30. So what the optimal value of alpha is here? 10? No. Alpha is 30 here because alpha should be greater than or equal to 30. On the other hand, we are trying to minimize alpha. So here the optimal value of alpha is 30. So what about here? Here alpha picks what? The largest value in the right-hand side, right? Here alpha picked 30. So here also alpha will pick the largest value for the right-hand side. And hopefully one of the pi's is the right value. And we know that alpha in the optimal point, if pi is the optimum, alpha is equal to this term. So if, for example, pi 2 is exactly pi star, then it means that alpha will take this value because the right-hand side there is the highest value we will take from this rank duality. Remember, the objective function of dual problem is always lower than the primal one, which is alpha here, except in the optimal point, which is equal to the dual objective function. Am I clear? Or should I explain again? So you agree that if we are lucky and one of these n guesses for pi provides the optimal pi, then we will have alpha equal to, for example, the right-hand side of the second constraint. Good. Are you happy with this approach or not yet? Is it straightforward to implement or not? Still, we need to have a lot of guesses for pi, right? We didn't really solve the problem yet. Still, we need to discretize and provide a lot of values for pi. And Makis said something nice. At least for x1, maybe we knew the lower and upper bound. Here for pi, even we don't know what the upper bound is. So pi could be anything. Good. So what we are trying to do before continuing, actually it's what we had schematically in our earlier slides. Each of these constraints, they are cuts. So for example, this cut is this one, this cut is this one, this cut is this one. So what we are doing, we are trying with this constraint to reconstruct the future cost, the function of future cost, or the future cost as a function of x1. Is it clear? Good. So remember, we also had the first stage problem. So far, we talked only about second stage problem. Now let me talk about first stage problem. So the only variable is x1. We have one constraint and the future cost. And now also we have future cost represented by this optimization problem for given pi 1, pi 2, 2 pi n. We can merge them, right? Both are minimization. Do you agree? We can merge them. So if we merge them, remember alpha is an auxiliary variable. So instead of alpha 1 as a function of x1, put alpha. Alpha is a variable. All these constraints appears here. So we will end up in this first stage optimization problem. And luckily now in the first stage problem, we only have alpha. We don't have a function of alpha. We have just a variable, single variable alpha. But we have to have a lot of guesses for pi. But this is our first stage problem, and we could reconstruct the future cost, or here alpha, variable alpha represents the future cost. Is it clear? If you write it's clear, I can continue. Very good. So here we assume that one of those pi's is equal to pi star, but we don't know if it's correct or not. As Maki said, we may need to generate 1 million pi. You are not happy yet, right, with this approach? Are you happy? Do you think it's elegant so far? It's not, right? Still, we have problem. We need to generate a lot of pi's. But remember, if we generate a lot of pi's, we solve this problem in one shot. It's not iterative approach. So let's think like the way Bender thought 70 years ago. Can we solve this problem in an elegant way iteratively? Any idea? Let's solve it. Let's solve it iteratively. So instead of having a lot of pi's at once, let's generate pi's iteratively a bit more in a more clever way. Can we do that? And the answer is yes. So as I said, we don't like this approach yet because we need to generate a lot of values for pi star. And as I said, this is one potential solution, but it's not elegant. We need to provide a lot of pi and then solve the first stage problem in one shot. But option 2, let's go for a systematic iterative approach. Let's say we are in iteration 1. Let's pick a trial value for x1 just in the first iteration. And then for the given value of x1, let's solve the second stage problem. So x1 is given. We can find the optimal value for x2 and for dual variable pi. What we can do next, we have pi here achieved in the first iteration. Now, instead of providing a lot of guesses for pi, let's use only one value for pi, the one we achieved from second stage. It's systematically achieved. So our second stage problem, again, alpha, remember, it's our auxiliary variable, what we saw in two slides, in the previous slides. The first stage constraint. So now, as you see, this is the cut we had, but only the pi comes from the second stage problem, right? As we did in the previous slide. So what we can do, we know that this alpha should represent the C2X2, the future cost. So we can check if this equality holds or not. Yes, we are fine. No, oops. No, we can go to the next iteration. Here we have updated value for x1. Now we don't need initial guess for, initial guess for x1. We have the updated value for x1 in iteration 1. So we can solve the second stage problem again for given x1, updated x1. We can calculate x2 and pi 2 in iteration 2. And again, we can repeat this. So what happened is that instead of generating a lot of pies, we generate one pie systematically in each iteration, and we add one constraint per iteration. So our pies generated systematically. Is it clear? Peter says yes. For everyone is clear, sounds that. So we will call this problem, the one we generate cuts, we will call it master problem. And the one that we achieve sensitivities, we call it subproblem. And the name of this approach is dual dynamic programming. Also, we call it Bender's decomposition. Let me take a few questions. Priyanka said, is there a better way to guess the starting value for X1 at the first stage? No. Good question. As much as you have a better guess, you need less number of iterations. But no, how can we guess X1 at the first place? Lisandro said, how we update X1? Solve this problem. In a master problem for given pi, we solve the first stage problem, its variable is X1. So by solving master problem, we have the updated value for X1, which is our complicating variable. In the next iteration, we give it to the subproblem. Adam asked, it's not clear for me why we choose pi k for all k and not, it's not clear for me why we use pi k. Good question, very good question. I think, yeah, I need to update the slides. No, wait. No, everything is correct. Because it's not I minus one. Here is I, because here I solve subproblem first and then master problem. It's the same. You can start, yeah. So here, yeah. If you say that here you are going to the next iteration, then it should be I minus one. If you say that you go to the next iteration here, then you keep it I. So yeah, correction. So I think the question of Adam, I think it's a good question, is that why we need to add a new cut? Why not to update cut, always to keep one cut in the master problem? I think this is your question, Adam, right?
Yes, also, but also I'm not like, I'm a bit confused why we're not just, you know, we're using PK for all i's. But like looking at the previous explanation, what I would expect is that we have like an i's, we have I number of or I minus one number of constraint.
Yeah.
But
for here I number.
Yeah, but for every constraint we use different pi. Like we just keep the pies from the previous iteration.
Yeah, we keep it. Exactly, we keep it. Yes, so in iteration one, we achieve pi one, you give it to here, right? And that's it. In iteration two, still you have pi one saved, but now you achieved pi two, now you create the second cut.
Oh, okay. Yes, all right. Yes, I see it now.
Yeah, but I think you can ask a better question. Why we keep the previous cut? Why not we eliminate the cut in the first stage only to have the cut from the second iteration? Do you have any answer?
Oh, not really.
Okay, if you do so, sorry. Remember the previous slide, I mean, yeah, here you need to add one cut per iteration. If you eliminate the cuts from the previous iterations, you are not reconstructing your future cost. Always you are representing your future cost by a single cut, which is obviously not accurate. So we need to keep the previous cuts too, just adding one per iteration. Hope it's clear. Let me get back to our slides here. and see what other questions we have. Nima said, because we might jump to another side of the minimum. Yes. Yannick asked, how do you know pi gets bigger than? What is your question, Yannick?
It was relating to the question before that we had, why you have to keep the cuts before.
Okay. So it was the answer. Very good. Nice. Any questions so far?
Yeah, I was wondering how you find like an initial starting value for x1, like if it's not easily seen by non-negativity constraints, how can you find one? Like if it's constrained by other constraints and...
Yeah, we don't know. Yes, exactly. We don't know. Just we know that we have to start with a feasible x1. If it's not feasible, if the second stage is not feasible, we can realize that it's infeasible. As I said, if your initial guess for x1 is not good, just you need more iterations, more cut to get the optimal point. But we don't have a systematic approach to find x1 in a more accurate way. No, we don't know. At least I don't know. But as I said, if our, let's say in our earlier slides, we have something like this, we know that optimal solution is here. If we start from here, of course, we need less number of maybe iterations. If we start from here, maybe we need a bit more iterations. Good. Brian said, why do you say that we do not recommend feasibility cuts? Yeah, at least it's my experience that you can add. So what happens if you saw that for given x1 the second stage problem is infeasible, we don't have pi, so you need to add here something that we call it feasibility cuts. I saw that it's sometimes it's really hard to get convergence with feasibility cut. Also, some of my colleagues confirmed that. So that's my recommendation based on my past experience from coding. If you like to go for that, no problem. But what I do, it's my trick is that to make sure the subproblem is always feasible by adding slack variables, then only stick to Bender's optimality cut. That's my own trick. No, I don't have any mathematical reason. For me, just sometimes it's really hard to converge. Sometimes it takes much more iterations. Maybe I had some mistake in my implementation, but also my colleagues confirmed. It's just based on experience. I don't have any mathematical reason for you. Priyanka says, can it happen that at some point you keep getting same value for pi, but different values for x1? Okay. Good question. Very good question. Yes. I will not call it parallel cut. I will call it inefficient cuts. Inefficient cuts. Usually it doesn't happen in convex problems, but yeah, I have to provide you some references. There are a lot of advanced variants of Bender's decomposition, and they are thinking, for example, how to generate more efficient cuts. As long as you provide more efficient cuts, you converge faster. So I'm not gonna teach the different variants of Bender's. If we see that we stuck somewhere, how to jump it, how to provide a better cut. Sometimes, but you have to be very careful, because if you generate one bad cut in only one iteration, you will keep it for all the next iterations, so you may end up in suboptimality, right? But there are a lot of elegant approaches how to make our cuts a bit more elegant, as I said. Remember here also in each iteration, I'm adding one cut. So you can call it conventional Benders or unicut Benders. So some people thinking of adding multiple cuts at each iteration, one per subproblem. Sometimes it works nice, sometimes it's not, because maybe in each iteration you are adding not one cut, but 10 million cuts. So your master problem may become computationally intractable very fast. Right. But if you check the literature, there are a lot of suggestions what to do with cuts, how to make it a bit more efficient. So if you see different forms of or advanced versions of Bender's, all of them, they are thinking of the Bender's cut, how to provide more efficient cuts or dense cuts, if you like to say. Johan asked, do we need all previous cuts or shouldn't be 2 cuts sufficient? No, we have to keep all of them. If you have only 2 cuts, it means that if you have this is objective function, original one, you are just, let's say, I don't know, okay, let me say like this. Johan, for example, this is your original objective function that you don't see. And if you have only 2 cuts, it might be something like this, and also in this point like this. So still you didn't achieve your optimal point. I think you have to keep your
Sure. There I
cuts.
agree, but don't you need, if you have 1 negative and 1 positive slope?
Yeah, if you have 1 here, if you have 1 here,
I guess the problem is more that you need to select which cut to keep, and that makes it maybe annoying.
Exactly. You have to do another optimization. Which 2 cuts are the most efficient?
Yeah, probably is.
It's not. Yeah, it makes it more complicated. But I agree with you. If you learn which 2 cuts are the most efficient, yes, of course, you can keep them and you can eliminate inactive cuts. I agree with you.
Okay, thanks.
Actually, that's one of the, I saw some papers also talking about that. Let's detect inefficient cuts or redundant cuts or inactive cuts and eliminate them to make sure our master problem is not becoming computationally hard. But good point. Priyanka said, thanks a lot. Some references would be helpful. Okay, I'll provide it for lecture tomorrow. I'll come with some references. Kelly said, so here we stop iterations when the lower bound becomes equal to the upper bound. Yes, exactly. Alpha comes from the master problem. It's the lower bound. And C2X2 comes from the subproblem, and it's the upper bound. So whenever alpha gets the same value or as close as possible value to C2X2, then we got convergence. Kelly said, so here we stop iterations when the lower bound becomes equal to the upper bound, whereas with Bender's before we stopped when their difference was small enough. Okay, so if you like, maybe then I can reword it as alpha minus C2X2, their difference is lower than or equal to epsilon. Okay, you can reformulate like that. Any other question? Mauricio said, do we need to add an error term alpha equal to C2X2 plus error to stop the algorithm? Which error, Mauricio?
Yeah, I was wondering, like, if we are comparing like the upper and lower bound, do we need to add like a kind of epsilon there? Yes, to
here?
stop and
were you here?
No, in the last kind of if-else statement. Yeah, I missed that. Sorry.
Yeah, I don't know exactly what you mean, but yeah, you can check if they are close enough or not.
Okay.
Yeah. Good, let me continue because I see that, yeah. So we call this dual dynamic programming, DDP, as Bender's decomposition. Remember from the beginning, if the Bender's guarantees obtaining the global solution of the original problem, if and only if the objective function of the original problem is convex with complicating constraints. Exercise 3 for tomorrow. Hopefully you will manage to do. Not to solve it, but just derive master and subproblem for this problem. So X3 is the complicating variable. It goes to master problem. while the rest of the problem should go to subproblems. And we have one subproblem per hour. So that would be amazing if you can formulate master and subproblems in this case. Thank you. I see the time is over. So I conclude the session and I stop recording, but I'll be here if you have any question about either about this lecture or the previous lectures or about your project. I'll be happy to answer. So let me stop the recording.